When discussing double integral, we usually discuss some bounded integration domain. And sometimes we want to integrate a function over some unbounded domain. So that leads to the improper double integral. To understand improper double integral, it's good to understand improper one-dimensional integral. So let me repeat this briefly. And the improper one-dimensional integral is the generalization of a definite integral. So if we start with the definite integral from a to b fx dx, then if the function f is continuous in the closed interval ab, then so is the antiderivative, and this is antiderivative evaluated at b, this is b, minus antiderivative at a. If these function values exist, no problem. The generalization of this definite integral is when the function f is continuous in the open interval only. That may happen in two different cases. Either if f is not continuous or not defined in a or b, or if a or b are plus or minus infinity. Then instead of fb, we consider limit of fx for x going to b from inside, and when a is less than b, then going to b from inside means from the left, and instead of fa, we consider limit of the antiderivative capital F for x going to a from inside, which means from the right. Now, can we introduce something in this sense for the two-dimensional integral? Yes, we can. If we have an integral over a set D, and if the set D is not bounded, then we can consider a system of finite disks, and we can consider the intersection of this unbounded set D with these finite disks. So in particular, let's consider the set Dn, which will be the disk with radius n. That means the set of all pairs xy from R2 such that x squared plus y squared is less than or equal to n squared. So for n is 1, this is the unit disk. For n is 2, it looks like that. For n is 3, the larger disk, and so on. And then we can define this integral as the limit of the double integral of the function fxy dx dy over the set which is the intersection of D with the nth disk, and the limit for n going to infinity. That means we look at the set at the integration domain D, and we only take one part, one portion that is not too far from the origin. And then we increase the n, the distance from the origin, and if this limit exists, then we say this is this integral. Well, in many cases, we don't use this. This is too complicated. We can use the Fubini Theorem. Namely, if we have the integration domain, which is the Cartesian product of the closed interval. Well, closed. Now we will use open interval, right? Cartesian product with the open interval CD. Then we will write it as two iterated integrals where y runs from C to D and x runs from A to B, or vice versa. And then if a or b or c or d is plus or minus infinity, then we consider the improper integral as a limit, and if it exists, then we say this double integral exists. Let us illustrate this approach to one quite surprising exercise. If we want to integrate the Gauss function e2 minus x squared dx, then we have not the antiderivative. Actually, sometimes we introduce the antiderivative and we call it the error function. But it is not possible to write the antiderivative in terms of elementary functions like powers and sine and cosine, logarithm, exponential, and so on. Surprising enough, if we consider a more complicated case, namely a related integral of two variables, then we will be able to write this. If we consider the integral over the whole plane r squared of the function e2 minus x squared plus y squared, it turns out that this can be computed, this can be found, and it will be related to this one. First, we can write this as integral from minus infinity to infinity, minus infinity to infinity, and this can be written as a product e to minus x squared times e to minus y squared dx dy. But here we have constant limits, so the integration domain is a rectangle, infinite rectangle in this case, and this is a product of something that depends on x alone times something that depends on y alone, so this can be written as a product of two integrals. In one of them we integrate over x, which is exactly this. In the other we integrate over y, but the name of the integration variable is not important. So we can rename it to x again, and we have that this is product of this times this. So if we call this capital I, then this is I times I. So after evaluating this integral will be square root of the result. And this can be computed because we can transform to polar coordinate system. If we use x is r cosine of alpha, y is r sine of alpha, then we have e2 minus x squared plus y squared is r squared. And instead of dx dy, don't forget to multiply by r. And we have dr d alpha, well, alpha runs from 0 to 2 pi, that means one whole term, and r now goes from 0, that's at the origin, to infinity, to cover all the plane. Well, and again, constant limits, product, so this splits into, a product of two integrals. Integral of 1, the alpha, from 0 to 2 pi is 2 pi. And we write the integral over r for the moment, from 0 to infinity, r e2 minus r squared dr. Now we can use the substitution. R squared is u, then 2r dr is du, and we have pi times, and 2r dr is du, so we have e2 minus u du. When r starts at 0, then r starts at 0 as well. And when r goes up to infinity, u goes up to infinity as well. Now that we did not copy just these limits, we recomputed it, and well, in this exceptional case, the result is the same. But this is not just a copy of this, and this is not just a copy of this. We recompute using this relation. 0 gives 0, infinity gives infinity. But now the antiderivative is minus e2 minus u, and infinity is 0, at 0 it's 1. So the result is pi. And because this integral is, or square of this is pi, so this is square root of pi. Isn't it nice? And when we have this result, we can write two more related integrals that are used in statistics, so we can prepare the results here. What do you think about this one? Integral from minus infinity to infinity, x times e2 minus x squared dx. Now, it looks more complicated than the previous one because we multiply by x. But for this, we can find the antiderivative. Or you can think that this is an odd function integrating over a symmetrical interval, so the result is, yes, 0. And what about integral of x squared times e2 minus x squared dx from minus infinity to infinity? This will be not 0 because we integrate a positive function, so it will be some positive result. And when we go back to our previous result, that integral from minus infinity to plus infinity e2 minus x squared dx is square root of pi, then when we replace x with some ax for positive a, then this does not change. So we have e2 minus, and instead of x, we write ax. A squared x squared a dx is again square root of pi. This is just a substitution. We can divide by a, and now this is true for all positive a, so we can differentiate with respect to a. And if we differentiate with respect to a, we get an integral from minus infinity to plus infinity, e2 minus a squared x squared, times the derivative of the inner function, which is minus 2ax squared dx. And on the right, this is a2 minus 1, which is minus a2 minus 2. And now, when we take a is equal to 1, and we multiply by minus, and we divide by 2, then we arrive to get rid of this 2, then we arrive at the integral from minus infinity to infinity, x squared e2 minus a squared x squared dx, which is square root of pi half. So this is a simple consequence of this result, of this integral. And we have computed this integral using the double integral over entire r squared using the polar coordinates. And then remembering that this is just the square root of this. So these results are used in statistics because this is the Gaussian function which is often used to describe distribution of some random variable that is a result of a sum of a large number of independent contributions.